Hello everyone, I'm Rajasri, Assistant Professor of Department of EEE, working at MLR Institute of Technology, Hyderabad. And in today's lecture, I'll be discussing single-phase half-wave controlled rectifier with RLE load. So this is a circuit diagram for single-phase half-wave controlled rectifier with RLE load. So where do we make use of this RLE load? E is nothing but EMF, that is in a practical DC motor where we have back EMF that represents this particular E, and if you see this particular DC motor consists of resistor as well as inductor as well as back EMF E. And if you see not just in DC motors, even a battery source consists of certain amount of EMF which also consists of a resistor as well as inductor. So the more practical applications are DC motors. And as we all know, this particular single phase rectifier with RLE load, rectifiers basically converts AC to DC. So the input is AC and output is DC. And here, this is the input voltage which is alternating in nature, which has got both positive half cycle as well as negative half cycle. So far, we have seen waveforms, and if you see here in this particular RLE load, we have this straight line which represents the EMF, E. So, the moment when Vs is equal to E. Why am I saying Vs is equal to E? See, if Vs is less when compared to that of E, in that case what happens? This voltage will be more positive. That means the cathode will be more positive when compared to anode. That means thyristor remains in reverse bias state, or we can also call it as off state. So that is the reason we can never turn on the thyristor when Vs is less when compared to that of E. And the moment when at this particular instant, say Vs is equal to E. Vs, we can write it as Vm sine omega t is equal to E. In that case, here we can write, and let us assume this instant at this particular where Vs it is becoming equal to E, I am naming this particular instant as theta 1. Let me name it as theta 1. And in that case, Vm sine of omega t axis is equal to, at this particular instant, it is theta 1 is equal to E, where theta 1 is equal to, it becomes sine inverse of E by Vm. So, this is the minimum angle which is required to turn on the thyristor. I mean, beyond which only we need to provide the triggering pulse, and below this particular angle we cannot provide the triggering pulse because the thyristor remains in off state. So, the instant when it reaches theta and beyond which, when Vs is becoming greater when compared to E, when this theta is exceeded and Vs is becoming greater than E, in that case what is happening? This particular thyristor anode is becoming more positive when compared to cathode. So that is the reason now the thyristor has come into the forward blocking state. That means it is ready to conduct now. At this instant called alpha, we are providing the gate triggering pulse. When we provide the gate triggering pulse at this particular instant called alpha, after having Vs exceeding the E, in that case thyristor is now come into the forward blocking state, and the moment when we provide the triggering pulse, this thyristor starts conducting current through the load, and that is how we are getting the output voltage across the load. That is from alpha to pi. See, whenever this particular thyristor is short circuited, whatever the voltage which we have provided, that is input voltage Vs, is being now applied to the load, and that is how we are getting the V output voltage waveform right from alpha to pi. And the moment it reaches pi, whatever the energy stored in the inductor, that is VL is equal to L into di naught by dt. And because of this particular energy stored in the inductor, the polarity is negative and positive. It is still maintaining the thyristor into the conduction state even during the negative half cycle. And during this instant, from pi to beta, output voltage is still present. Whatever the energy stored in the inductor is now circulating through the thyristor to the load. And that is how we are getting the output current. And if you see at this instant called beta, inductor is completely exhausted and there is no energy remained in the inductor, and that is how the thyristor is now turned off, and the net voltage across this particular output load is V0, that is E, is equal to E. And again at this instant called 2 pi plus alpha, we are providing the triggering pulse such that thyristor is again on and it started conducting current through the load till 3 pi plus beta. And now coming to the output current, if you see right from here to here, there is no output current which is flowing through the load. The moment at the instant when we provided triggering pulse at the instant called alpha, thyristor started conducting, and because of the presence of the inductor, current will be building at a slow rate, and it has become maximum at this instant called pi, and this is theta 1, and it is conducting till beta, that is beyond pi. Because of the energy stored in the inductor, since it is dissipating a current through the load, that is how we are getting the output current right from pi to beta. And once the energy stored in the inductor is completely dissipated, the output current becomes 0. And again at this instant called 2 pi plus alpha, the thyristor started conducting, and because of the inductor, we are getting the current flow right from this instant, that is 3 pi to beta. So now coming to the thyristor voltage across the thyristor waveform, if you see, since thyristor will not be getting turned on until Vs is greater when compared to that of E, and at the same time, the moment when we provide the triggering pulse, only the thyristor will be on. Until then, we will be getting the voltage, and which is just similar to that of Vs. The voltage across the thyristor will be Vs, and the moment when triggering pulse is provided, since thyristor is on, the voltage across the thyristor will come down to 0, and it remains 0 as long as thyristor is conducting. That is, thyristor will be conducting till beta, the voltage across the thyristor will be 0. And at this instant called beta, again now thyristor is off, and because of which whatever the voltage across the source will be appeared across the thyristor, and that is how we are getting thyristor voltage till this instant, and again the cycle repeats. This is the voltage waveform across the thyristor. Hope now you have got a clear understanding. And let us derive the expression for I0. For that, let me consider the circuit diagram here, that is single phase half wave rectifier with RLE load, and this is the AC input which we are actually providing. In this case, we get, if we apply KVL for this particular circuit, in that case we get Vm sin omega t. So I am taking it as Vs is equal to, I am substituting Vm sin omega t, which is equal to, by applying KVL, we get R into I0, plus voltage across the inductor is given by L into di0 by dt plus EMF. And here, if you see, we have got this as steady state term, and even this is steady state term, and this is transient term, transient component of current. So here, this is IS1 and this is IS2. And if you consider, we have I0 output current is equal to, it is the summation of steady state current plus transient current, where in this particular equation we have got two steady state terms, that is IS1 plus IS2 plus transient term, that is IT. So in this case, let me see what is IS1. IS1 is equal to Vm by Z sine of omega t minus phi, whereas IS2 is equal to, if you see, current, if at all, if EMF alone, this voltage source alone is present, in that case current will be flowing in this direction. In that case, IS2 will become minus E by R. And now, transient component of current, IT is equal to, it is given by the transient component of current, it is because of the inductor, and we get A into e power minus R by L into T. R by L into T. This is a transient term. And if you substitute all these equations in this particular I0, in this particular equation 1, we get I0 is equal to, IS1 is Vm by Z sine of omega t minus phi minus E by R, that is IS2, and here in equation 1 I am substituting, plus transient current, that is A into e power minus R by L into T. And in order to obtain A, let me assume the condition for waveform where omega t is equal to alpha and I0 is equal to 0, so that I can obtain the value of this A. In that case, I get I0 is equal to 0. I am substituting in this particular equation, I0 is equal to 0, which is equal to Vm by Z, where omega t is equal to alpha minus phi minus E by R plus A into e power minus R by L. Here, omega t is equal to alpha. In that case, t is equal to, it becomes omega by alpha. So, R alpha by omega I can write. And from this, I am obtaining the value of A, where A is equal to, we get, I am taking this minus that side. So, we get E by R, and this is taken that side, minus Vm by R into sine of alpha minus phi, and since I am taking this that side, e power, that side becomes positive, that is R alpha by omega L. And substituting this equation A in this current equation, we get I0 is equal to, I am writing directly Vm by Z. I0 is equal to Vm by Z sine of omega t minus phi minus sine of alpha minus phi into e power, taking minus R by omega L common, we get omega t minus alpha minus E by R into 1 minus e power minus R by omega L into omega t minus alpha. This will be the equation for I0. Since we have got I0, let me obtain I naught average, which is equal to 1 by t, 0 to t, Vm of omega t, V naught of omega t, where V naught is equal to, I am writing this as 1 by 2 pi. This is the total time period of the waveform, and it is actually conducting. That is, we are getting the waveform right from alpha to beta, which is equal to Vm sine omega t minus E by R into omega t d omega t. So this is nothing but your I naught average expression. Similarly, I naught RMS 1 by t conducting from alpha to beta. This is Vm sine omega t minus E by R whole square into d omega t whole to the power of 1 by 2. And coming to the circuit turn-off time, this will be, it is conducting from 2 pi to beta. So that is the reason 2 pi plus theta 1 minus beta by omega. It is conducting between 2 pi and beta. So that is the reason this is the circuit turn-off time we get for single phase half wave rectifier with RLE load. And in the coming up lecture, we will be seeing problems. Thank you.